Question about our labs, if you have a second.
Yep.
So the Jupyter notebooks, will those not be due the day of the lab now? Like, are we just using those to help us with the report?
So I'm not giving you any Jupyter notebooks, so you're gonna have to make your own and do your own data
Do you
analysis.
want to see them?
No, what you'll do is you'll like print out the results of those and paste the plots in your notebooks. So you're only submitting them.
Right.
Yeah.
Thank you.
Yeah.
Just saw it for went from the year to work. Oh my god. Absolutely mad. Like everyone got the great year, bro.
Great. It's the first ride, so it's last time. I was like, I'm not. I was like, I'm not like. And I got absolutely taken off.
Oh, you got fly.
I didn't think I had anything, but.
Yeah, should have gone. Nice.
Oh, yeah, I got there at.
All right, so hope everyone's having a good morning, had a good week of, first week of classes, ready for a frigid weekend. All right, so we didn't do too much last time. We just talked about kind of, logistics and fun stuff like that. What we were getting ready to do was to try to work on this so-called Fourier series problem, where we're going to take some periodic function. It could have whatever shape you like. And then we're going to try to, the only restriction is that it has to repeat after some time, capital T. And so here I just made some arbitrary thing that looks like it's repeating. And the claim is that we can express any periodic function as an infinite series of cosines and sines. And our task is then to figure out what are the values of all these coefficients, A0, A1, A2, A3, and so on, B1, B2, B3, so on. And so there's an infinite number of these coefficients to determine. And so we're going to try to find all infinity of them today. Okay, so we need to find those coefficients. Now, before we do that, what I thought we would do is kind of just listen to some waveforms from some different instruments that are available. These sounds are taken from this URL, some Colorado, I don't know, math website. So I've linked this website on the course webpage, so you can go there and take a look at what they have. And so they have a bunch of different sounds, and I'm just going to play some of them for you. So let's see if this works. Let's see if you can, first of all, hear this. Yeah, okay, good. So the first thing I'm going to do is I'm going to play the note A, just with a tuning fork. So let's see if this works. So that's the note A from striking a tuning fork. Okay, so that's fine. And then what we're going to do is let's just quickly go back here and I'll show you. If you were to measure the waveform from a tuning fork, and so what sound is like you strike a tuning fork, right? And then the little tongs on the fork vibrate and then they cause pressure variations in the air that travel to your ear, cause little hairs in your ear to move around and make some nerve signal that goes to your brain. But whatever, if you were to measure the pressure variations near the tuning fork with some device, a pressure device, you would get this almost perfect sine wave. Okay. What you could also do is you could try to measure at what frequencies is the air oscillating. And you could construct a plot where you get spikes at all the different frequencies that the air oscillates at. And the height of the spikes tells you the relative contribution, like the strength of that pressure variation at the different frequencies. And so that's what that plot is here. So what you see here, this is a log scale. So this 10 to the 0 is like 1. And over here, 10 to the minus 4 is like 1 over 1,000, 0.0001. 10 to the 4 is 1 over 10,000, sorry, 0.00001. So this is 10,000 times stronger than something over here. Okay, so if you were to make that kind of measurement with the tuning fork, what you get is one strong spike at what's called the fundamental frequency. That's the frequency of the note. It happens to be an A. But then you get little spikes at other frequencies as well. But those are so small in contribution that really what you see is almost a perfect sine wave at this fundamental frequency. That's a tuning fork. When you listen to music, music made out of pure tones does not sound very appealing to ears, okay? And so what we're going to do is we're going to look at different instruments. What's the next one? A flute. So I've got a flute here. It's going to play the same note as the tuning fork. It's just made by the flute. Okay, so the sound is a little more kind of dynamic or warm or whatever. Like, I'm not a musician. I don't know what terms people use, but it's a fuller sound. Okay, even though it's playing the same note. If you were to measure the pressure variations kind of near the, that whatever that output of the flute, what you get is something that's periodic again, but it has more structure. Okay, it's not a pure sine wave. It actually looks like there's this little double oscillation, and then it kind of shoots down, and then that repeat double oscillation shoots down, double oscillation shoots down. If you were to make the other measurement where you look at what frequencies is the air oscillating and what are the relative strengths of those oscillations, now you get something with a lot more structure. Okay, so there's a lot more frequency contributions, but notice that it's not continuous. It's not all the frequencies. There's a spike here, and then it goes down to almost nothing, and then there's another spike. And in fact, the spikes are almost equally spaced from one another. So these things are called harmonics or overtones. So there's a fundamental frequency, and then there's twice that frequency, 3 times that frequency, 4 times, 5 times, 6 times. Those are all the harmonics. Okay. And if you go and look at how our proposed Fourier series is constructed, there's this term would be at the fundamental frequency, but then there's the harmonics at twice the frequency, 3 times the frequency, 4 times, 5 times, and same for the sine. Fundamental, 2 times the fundamental, 3 times the fundamental, and so on. And so what we're trying to do is we're trying to make some function that's going to allow us to reproduce this type of thing. So this, and it's not just the flute, there's lots of instruments. What's the next one? The next one is a violin. Here, I'll show you the violin one before we hear it. So again, it's periodic, but it's not a sinusoid and doesn't look like the flute, right? It has some more complicated, different structure. But when we look at the harmonic contribution, the same harmonics contribute, but there are some differences in the relative heights, right? The fundamental is the same, but the second harmonic in the flute was strong and it's weak for the violin. But then when you go up to these higher frequencies, there's more stronger contributions from the higher frequencies in the violin than there are from the flute. Okay, so anyways, we'll hear the flute, I guess. Where is it? Oh yeah, that's, oh, sorry, we're looking for violin, right? Yeah, you're right. Okay, whatever, it sounds like something. And then this is a singer. And people are less good instruments than other things. And so when you look at the voice of a singer, you know, it has some complicated shape when you measure pressure versus time. But when you look at the harmonic structure, it produces fewer harmonics than these other instruments. And, you know, there's nothing special about these instruments. We could have chosen a cello or a piano or a guitar or whatever. It would all have that similar sort of structure. Okay, so anyways, that's a little bit of motivation for why we're looking at some of these stuffs, or at least one application where some of this could be useful. All right, so I guess I just wrote down some notes. This is probably just what I said in words. Waveforms measure the pressure versus time of the signals of various instruments playing the same note. And then the frequency spectrum shows which frequencies the air pressure is oscillating at and the relative strengths of the oscillations at those different frequencies. Okay, so now we want to get back to our Fourier series. Fourier series. Okay, so our claim is that our periodic function is going to be written as a over 2 plus a1 cos x plus a2 cos 2x plus and so on. And then there's the b1 sine x plus b2 sine 2x plus and so on. All right. To find the coefficients, what we're going to end up doing is evaluating a set of integrals. Okay, and so let's see if we can find the first coefficient. So to find a0, let's try evaluating the following integral. Okay, so the integral that I want to look at is the integral of f of x from minus pi to plus pi. Okay, and we're going to assume that our periodic function is going to be have a period of 2 pi, the way we've constructed this thing, right? Because if x is equal to, you know, 6, and then we look at 6 plus 2 pi, then the cosine function would just repeat it. So it's definitely periodic on an interval of 2 pi. And so in fact, the integral I'm going to look at is 1 over pi times the integral of minus pi to pi of f of x with respect to dx. And to evaluate this, we're going to take this long expression and we're going to sub it into this f of x, and we're going to see what we get when we do that. So this long expression goes into our f of x. And so what we end up with is 1 over pi, and then we're going to have a whole bunch of integrals. So we're going to have the integral from minus pi to pi of what? A0 over 2 plus the integral from minus pi to pi of a1 cos x minus pi to pi of a2 cos 2x. There's a bunch more cosine terms, so 3x, 4x, 5x, 6x, all those terms. And then we're going to have a b1 sine x dx plus b2 sine 2x dx, and then a whole bunch of other terms. Okay, now I don't actually want to do all these integrals. They're not hard. We could just do them all, but I think we can be a little more clever instead of actually evaluating the integrals. Let's plot cos x on the interval from minus pi to plus pi. So cos x is 1 at 0, and it's 0 at pi by 2, and it's 0 at minus pi by 2. And so let's see if I can draw cos. And then it's going to go to minus 1 over here. And so it's going to look something like this. Okay, so this is going to be 1 over here, and this is going to be minus 1 over here. And so cos x looks something like this. It's not a perfect drawing, but it's pretty decent. All right, so if I was to integrate cos x from minus pi to pi, what I'm going to be doing is I'm going to be adding up the total area between the x-axis and the curve, right? That's what an integral does. For any areas that are above the x-axis, we're going to count that as a positive area. And for anything that's below the x-axis, that's a negative area. And so maybe positive areas could be red, and maybe negative areas could be blue. And so if I add up all the negative and positive areas, what do I get? 0. Right. So that tells us right away that this one's going to evaluate to 0. If I did cos of 2x, I would have the same shape, but it would have to oscillate twice between minus pi and plus pi, because the period of a cos 2x waveform is just pi. So this 2 pi range is 2 periods. But if I integrate something that has exactly 2 periods over the range, what am I going to get? 0. We're still going to have half the area positive, half the area negative. Okay, same thing for 3x, 4x, 5x, 6x. All of the cosines are going to just vanish. You could probably see it already, but we can make a similar argument for sine x. Now sine x is going to be 0 at x equals 0. It's going to be 1 at pi by 2, and it's going to be 0 at pi, and it's going to be minus 1 at minus pi by 2, and it's going to be 0 at minus pi. And so if we were to draw the sine function, it would look something like this. I didn't draw. Oh, I know why it looks so stupid. It's because I didn't have my intervals spaced properly. Here, minus pi by 2 is over here, and this is minus pi. Okay, so there we go. That'll look a little bit better. Okay, and then the same thing, I could color the positive and negative areas different colors. So let's see, I use red for the positive areas, blue for the negative area. And so it's pretty clear that those two areas are the same size. And so the sine x integral is also going to just vanish. And sine 2x would vanish, and 3x and 4x and 5x, and everything vanishes. And all that's left is the first term. Okay. So only the first term in the integral survives. And so what we have is that 1 over pi times the integral of minus pi to pi of f of x dx is 1 over pi. There was an a0 over 2, but those are constants. I can pull that outside the integral. And then we have minus pi to pi of dx. And all the other terms vanish. And this is now a trivial integral. Dx just integrates to x between pi and minus pi. And so that range is 2 pi. But we have 2 pi here, and we have 1 over 2 and 1 over pi out front. And we end up with a0. So therefore, the a0 coefficient is determined from the integral a0 is 1 over pi, the integral of minus pi to pi f of x dx. Okay, so we have found one of the infinitely many coefficients that we need to determine. We're going to do similar things to find the other coefficient. So what I'm probably going to do is I'm just going to tell you what the result is, and then we'll go and do a proof of at least part of the proof anyways. So here's the next claim. So claim number 1, I guess, would just be that Fourier series expansion that we wrote down. We haven't proved it yet, but we found one coefficient. Claim number 2 is that all of the other coefficients for A, so this would be an for n equals 1 up to infinity, just not the a0 one. That's going to be equal to 1 over pi times the integral from minus pi to pi of f of x. And then, so if I put a dx here, that would be the a0 one that we did. We're going to add something in here. And what we're going to add in is cos nx. And the next part of the claim is that if we wanted to find the bn coefficients, what do you think it's going to be? Sine, yeah, that's right. So where n is going to be 1, 2, 3, so on. Okay, so you can maybe see what's going to happen is if we evaluate these things in the same way we just did for the a0 coefficient, what we're going to do is wherever we see f of x, we're going to sub in this big, huge thing. So we're going to have cos x, cos 2x, cos 3x, cos 4x, sine x, sine 2x, 3x, and so on. And for example, if we're doing the an coefficients, we're going to end up with things like cos x times cos nx, cos 2x times cos nx, cos 3x times cos nx, sine x cos nx, sine 2x sine nx, cos nx, and so on. And so we're going to have all these integrals to evaluate that involve products of different kinds of trig functions. So when we sub in f of x is a0/2 plus the sum of an cos nx plus bn sine nx sine nx. We end up having to evaluate integrals like, it's going to be things like cos mx times cos nx. So we'd have integrals like this. We'd have integrals of something like sine mx cos nx. And then we might have some that involve, well, not might, we would have some that involve like sine mx times sine nx dx. Okay, and so what I'd like to do is develop some tools or just some prescriptions where we don't have to evaluate all of these individually. Let's just come up with some general rules. So let's see what we can do here. So what we want to do is I want to consider the integral. Let's see, let's do 1/2 pi integral from minus pi to pi of sine mx cos nx dx. So we're going to consider this middle case first. Okay. Now we probably could just try to use, like, for example, we could find identities for the products of trig functions and so on. What I'm going to do is I'm going to convert these trig functions into exponentials, because taking the integrals of exponentials is very easy, even when you have the product of exponentials, because if you have the product of two exponentials, you could write that as a single exponential where you just add whatever's in the argument. So this is easiest to evaluate if we consider, or if we express the trig functions as complex exponentials. So let's recall Euler's equation. Euler's equation, remember, was that e to the jx was, let's do plus or minus jx. Okay, if you like I better, we can do I. We're not in electronics anymore, so we don't get confused with current, but I always use j just because I'm used to it. But e to the jx was cos x, and then it was plus or minus j sine x. So if you take the plus sign here, you take the plus sign here. If you take the minus sign here, you take the minus sign here. Okay, so if we were to then consider the following, we could say e to the jx plus e to the minus jx is going to be equal to what? Well, plus or minus doesn't affect the cosine. So if we add these two, we're going to get two cosines. But then for the sine term, when we take the plus one, we'll get plus j sine x. When we take the minus one, we'll get minus j sine x. Those will cancel. So this is just going to be 2 cos x. And so therefore, we could write cos x is equal to e to the jx plus e to the minus jx divided by 2. Okay. Likewise, we could find that sine x is e to the jx minus e to the minus jx. when I subtract the minus jx, the cosine terms will vanish, but I'll get two j sine x, so I have to divide by two j in this case. Okay. Fair enough. So what we're gonna do is we're gonna go back to that integral, and for sine mx, we'll put in this thing. We'll just have to put in an m here, so wherever x is, we'll have mx. And for the cos nx, we'll put in n times x wherever we see just the x. All right, so therefore, 1 over 2 pi, the integral from minus pi to pi of sine mx cos nx is going to be what? 1 over 2 pi integral minus pi to pi. We're going to have e to the j mx minus e to the minus j mx divided by 2j. That's the sine mx. Then we'd have e to the j nx plus e to the minus j nx divided by 2. And that's the cosine. Okay. Now, if we multiply all this stuff out, we're going to get 4 terms. I don't want to integrate 4 terms because they're all going to be pretty similar, right? When I multiply these two, I'll get e to the jx times m plus n. But m and n are just going to be integers, so m plus n is just some integer. When I do this one times this one, I'll get e to the jx times m minus n. M minus n, again, is just some integer. Here we'll get an n minus m, some other integer. Over here, we'll get minus m minus n. It's still an integer, it's a -1, but it's still an integer, okay? So if we multiply out all the exponential, I don't know, terms, I guess. We get 4 terms of the form e to the j kx, where k is an integer. Right, so we'll have terms where k is m plus n, or it's m minus n, or it's n minus m, or it's minus n minus m. But it's just all integers. So what I'm going to do is I'm just going to evaluate that integral for some arbitrary integer and then say the result applies for all of these 4 possible cases. Okay, so let's see what happens when we do evaluate this integral. I also don't really care about right now the 1 over 2 and the 1 over 2j. Those are constants, and we just pull them outside the integral. They're not going to matter, and we'll see why in a second. So the beauty of doing this is now I don't have trig functions in here. I don't have to worry about like using identities for products of sines and cosines or whatever it is. I just evaluate this integral of this exponential. What's the integral of e to the j kx with respect to x? E to the j kx, and what am I missing? Yeah, it's a 1 over jk, right? Okay, so then that's just equal to 1 over 2 pi, 1 over jk, e to the jk pi minus e to the minus jk pi. That's beginning to look familiar. What does this look like? The cosine has the plus here, so it looks like the sine. We'd have to have a 2j here, but it would be sine k pi, where k is integer. But what's the sine of any integer multiplied by pi? I don't think I've heard the right answer yet. Sine of, what's the sine of pi? 0. What's the sine of 2 pi?
0.
Sine of 3 pi, sine of minus pi, sine of minus 2 pi. They're all 0, right? I don't care what k is, as long as k is integer, this is going to be 0. And so k can be any one of those 4 combinations, positive or negative, it's always going to be 0. Okay, there's one caveat here, and the caveat is, well, what if k was equal to 0? Then we would have a problem because we divide by 0. So this is the case that we're thinking of here of the m not equal to n case. Oh, sorry. M not equal to n case. Okay, and that just prevents the possibility if m and n were equal, both of these cases would be k equals 0. So we've done one possible case. Okay, and so then we get 0 for this case. All right. Well, let's do some of the other cases. What if m was equal to n was equal to 0? That's an easy case. Okay, so then we would go back to the original integral here. If m is equal to 0, what's sine of mx? 0. And then cos would be 1. So you have 0 times 1, you have the integral of 0. And so there's no area underneath and function just equal to 0. Okay, so here we would have that sine mx is equal to 0, cos nx is equal to 1. And so therefore, the integral that we were considering would just be equal to 0 because the sine is equal to 0 in this case. Okay, so we've considered 2 cases. Now the remaining case is m is equal to n, but they're not equal to 0. If we consider that case, then we've considered all possibilities. So the m is equal to n, but they're not equal to 0 case. Okay. Well, let's see. We'd have 1 over 2 pi, the integral of minus pi to pi. And then we would have what? E to the j. Let's use n, I guess. We're going to say m is equal to n. Minus e to the minus j nx over 2j. So this is the sine of mx when m is equal to n. Okay, so there's the sine. And then now we have to put in the cosine, e to the j nx plus e to the minus j nx over 2. And this is just cos nx. Okay, and let's just multiply these things out this time. I don't want to, in this case, just say they're all of the form e to the j k, because when we integrate, we'll get a 1 over k, and if m equals n, sometimes k will be equal to 0, and we'll have a problem. So let's just see what happens if we do this one carefully. All right, e to the j nx times e to the j nx. So that's e to the 2j nx. Then we have e to the j nx plus, times e to the minus j nx. So that's going to be at e to the 0, which is a 1. Then we have minus e to the minus j nx times e to the j nx. That's going to be minus e to the 0, which is a -1. So that +1 and the -1 are going to cancel. And then we have minus e to the minus j nx times e to the minus j nx. That's minus e to the minus 2j nx. And I guess we would still divide by a bunch of stuff. I guess it would be 4j here, dx. And then these things are going to cancel. All right. So what's e to the 2j nx minus e to the minus 2j nx? So a complex exponential minus the same complex exponential, the negative here, yeah. Sine, yeah, this one's going to be the sine. We have an extra 2 in the denominator. So this would be sine of 2nx divided by 2, I think. And so that what we end up with is 1 over 4 pi, integral from minus pi to pi of sine 2nx dx. What could you tell me this integral is going to evaluate to without actually doing the integral? 0. Why? Yeah, that's right. So it's the same argument we made before. If we were to actually plot this thing, the function would be half the time negative, half the time positive over this interval. And so that would have to be 0, since sine 2nx is, let's just say, symmetric about the x-axis on the interval minus pi to pi. Okay, so now we've considered all possible cases, and in every single instance, we've got zeros. So what we can conclude, therefore, is 1 over 2 pi, the integral of minus pi to pi of sine mx cos nx is equal to 0 for all possible m and n. That's a useful piece of information because when we go back to here, where the hell is it? When we go back to here, we're going to have a bunch of terms that have this kind of integral. And whenever we see a mixture of sines and cosines, we can all immediately just say that's going to integrate to 0. We still have these ones to consider. And I'm not going to do them for you. In fact, you'll do one of them, I think, in a homework. So let's see. So we can likewise show that, okay, the other kinds of integrals that we'll run into are products of sines and these ones aren't so direct. They're not all 0 like we did for sine times cosine. We're going to get a 0 when m is not equal to n. Okay. And let's say, maybe I should be a little more careful. Let's say m is not equal to n is not equal to 0. Okay. We're going to get a 1/2 for m equal to n not equal to 0. And we're gonna get a 0 for m equal to n equal to 0. So I guess I didn't have to have a not equal to 0 here, but I'm just gonna separate out the 3 possible cases. So one of them is not equal to 0, and it's when m and n are equal. Okay, you could probably actually imagine why. This one's not so easy, it's not so difficult to think about if you know your trig identities. If this was an n, we have sine nx times sine nx. What's the trig identity for a product of identical signs? What's sine x times sine x? Yeah. So then what's the identity for sine squared? Yeah, that's right. I think it's a minus sign for the sine. I think it's 1/2 of 1 minus sine of 2x. So if we have sine nx, it would be 1/2 of 1 minus sine of 2nx. When we integrate, the sine 2nx will vanish. That will have no area. But then we have 1/2 times 1, which is where that 1/2 comes from. Okay. The other one that we would have to worry about is the integral of cos mx times cos nx dx. And that's going to be, we'll get 0 when m is not equal to n is not equal to 0. We'll get 1/2 when m is equal to n not equal to 0. Again, you could easily think about that one, because if m and n are equal to 0, we're going to get cos squared. Cos squared would be 1/2 of 1 plus cos of 2x. The cos 2x thing will integrate to 0, but we're going to be left with the 1 times 1/2, and there's the 1/2 again. And then we have m is equal to n is equal to 0. That's also easy to think about, because if n is 0, we get cos of 0, which is 1, times cos of 0, which is 1. And so we get the integral of 1 from minus pi to pi, gives us 2 pi, cancels the 2 pi, and we're going to get a result of 1. We could do the same thing for the sine, because if I put in zeros here, we'll get sine of 0 times sine of 0, which is 0, integrate to 0. Okay, so this is one important result, and here's important results 2 and 3. And you're going to do 2 and 3 for homework. Okay, so 2 and 3 will be homework. And then let's check time. How are we doing time-wise? We have 5 minutes left. Okay. Let's see if we can go back and look at where did I put it? Sorry, I gave you the results somewhere, didn't I? Sorry, let me just find it. It's way back at the beginning. Okay, let's see if we can do the AN version, okay? Let's try to evaluate 1 over pi, the integral of minus pi to pi of f of x cos nx dx. Okay, that's going to be 1 over pi, and there's going to be a whole bunch of crap. Okay, so f of x, we have to remember it had an a0 over 2, and then we have to multiply by cos nx dx. And then we had like an a1 cos x times cos nx dx. Then we had an a2 cos 2x cos nx dx. There'd be a bunch of terms, and then I'm going to write in a special one. We're going to have an an cos nx cos nx dx. This is the m equals n case. That will be a special one. And then there'll be some more cosine terms. Then we would have minus pi to pi of, we'd have a b1 sine x cos nx plus b2 sine 2x cos nx plus some more terms plus minus pi to pi bn sine nx cos nx dx plus and so on. Okay, so there's a crap load of integrals to do here. But we could start knocking some of these off. What's the integral of the cosine function? 0. We've done that a bunch of times already. That one's easy. This one's going to be 0 for sure. Okay, let's do the ones that involve a mixture of sine and cos. So a mixture of sine and cos is always 0. It doesn't matter what m and n are. Okay, so wherever we have sine times cos, this is going to be 0 by 1. This is going to be 0 by 1. This is going to be 0 by 1. All right, so we knocked a bunch of those things off. And then we have some cosine times cosine terms. Okay, cosine times cosine. If m and n are not equal to each other and not 0, we're going to get zeros. Okay, all right. So here's m equals 1 and n not equal to 1. So this is 0. Now, is that by 3? Yeah. So this is 0 by 3. Here's m equals 2 and n, some arbitrary integer, not 2. So that's going to be 0 by 3. All of these things are going to be 0 as well. All of these things are going to be 0 as well. And there's only one term that's surviving. It's cos times cos when m and n are equal to each other. And we said that that was going to be a 1/2. It's a 1/2 if you're dividing by 2 pi. So we're not dividing by 2 pi here. So it would be 2 pi divided by 2. And so overall, this is going to be a pi. So we would say this one here is going to be 2 pi times 1/2 by 3. And so now we've done every single integral and we're out of time. So let me just write down the final results. We say, therefore, the integral we were working on, 1 over pi f of x cos nx dx, from minus pi to pi is equal to, so there was a 1 over pi, and then the 2 and the 1/2 are going to cancel, times pi. I forgot one thing here. What am I missing here? A, yeah, exactly. So this is all multiplied by an. And so we would get pi times an. And of course, the pi cancels. And so this is equal to an. All right, so we now know the A0 coefficient. We know how to calculate the AN coefficient. In a homework, you'll do the BN coefficients that involve sine. It's the exact same similar argument that we just did. So we're gonna know how to calculate all the coefficients. What we'll start with Wednesday is the next time we meet, is we'll actually do an example. So this has all been abstract. We'll make it not abstract and see how we can apply this to some actual periodic functions. All right. Thanks very much. Have a good weekend. Yeah. Where here? Oh, yeah. Oh, this right there. Yeah, yeah.
By the time we finish that pool again, go and check and make sure that my water main doesn't froze.
Yeah, the clutch on my car was very slow.
Oh, yeah,
Yeah.
yeah, no, I pressed mine down, it probably took about 2 seconds.
Yeah.
I love those bolt starts for the motor stuff, like with those blind cars.
Yeah, I grew up in Winnipeg and we, all those cars there have block heaters, so you plug it in.
Yeah.
Keep the oil pan nice and warm.
It's something that I probably should have done, but I don't have a block here. in my
Yeah.
truck. I don't follow. I don't have the equipment or at least I have a block here built into the block.
I see.